a very good analogy that they told us on our first day of class that I still remember for, what is process control, or can you think of a scenario where you're doing it, is to imagine that you are taking a shower. And so if you turn on your shower, you might have a shower that has like a hot and a cold valve, or you might just have a one valve thing, but let's go with the two valve thing for the sake of this example. Do you like to take cold showers? Probably not. So most people, they like taking showers that are around some kind of temperature. Ideally, it's probably, call it 100 degrees Fahrenheit. And so basically, the temperature that you want your shower to be at is what we call a set point. So that's basically this desired output of your process. And so that's what we would call an output. And you can have multiple outputs in a process. So maybe you don't just want to have 100 degree temperature water. You also want to make sure you've got a good flow rate. Like, you don't want to have just a little dribble of water. You want to have a lot of water. So, you can get really advanced really quickly and start having even more outputs you're trying to control in your process. But, for the sake of just a really simple approach to learning this stuff, typically you're going to start with doing one input, one output, or SISO, single input, single output systems. But that's the gist of it. And so, I want to take a shower. I want the water to be at 100 degrees Fahrenheit. And so the human in that situation, in that loop, so to speak, is the controller. And so basically what you do is you go in the shower and you turn the knob, and you turn the cold and the hot water knobs, and eventually you figure out where does the water temperature feel right to you. And so, you've got thermoreceptors in your body. Those are the sensors that are really detecting whether or not you like what the temperature of the water is. Is that within the set point that you care about? And if not, then you change these things. You change the inputs in your system. And so the inputs in this system that we're working with right now would be like the hot water valve, how open that is, and the cold water valve, or how open that is. And so those are the inputs in this process that we have. And so, let's say at steady state, everything's wonderful, and there's no difference between the desired set point of the water, which is 100 degrees Fahrenheit, and what the current temperature of the water is. And so this is perfect. Like, you're happy, you're taking your warm shower, and everything's good. And then let's say that your brother goes in your house and, turns on the toilet. What's going to happen? And hopefully intuitively we know that when there's this drop in the pressure of water, specifically cold water, but we keep the flow rate of our hot water constant, the water temperature is going to get really hot really quickly, and it's going to scald us. And so in this situation, what happened is that there was a disturbance variable, a disturbance input into our process. And you model this with these things called step functions. So basically, step functions are really simple. They're just like, it's 0 and then it's 1. And so as soon as your brother, turned on the toilet or flushed the toilet, that's right when that disturbance variable happened. And then you can have this thing called dead time, which would be, let's say it's not going to be immediate because, it takes time for the lower cold water pressure to make its way to the actual shower. So there's going to be some dead time, there's a delay between when that happens and when you actually feel or get scalded by hot water. And so that's another thing that's going to be relevant in what goes on in these processes. And so if you're going to look at something called a feedback controller, what's happening in this situation is basically you're going to have to be affected by this change in your output, which is the water temperature, before you realize I need to change an input here. And so in that case, what you would do in the shower is that you would realize, oh my God, I'm going to go get scalded. So you can either do one of two things or three things. So you can either decide to open up the cold water valve even more to try to let as much cold water through as possible to maintain or to cool that water down. You can also decrease the amount of hot water that's coming out by closing that valve slightly, or you can do a combination of the two. And so you are the controller in this process, and you are acting as a feedback controller. You are specifically responding to this thing called error. And so error, E-R-R-O-R, is the difference between that set point value, which you want your shower to be 100 degrees, and the current output of the shower, which in this case is something like, let's call it 110 degrees Fahrenheit, because of the fact that the cold water pressure just dropped in your house. And so you're responding to air. And so PID controllers are the types of controllers that in a process control class you learn how to optimize. And there's 3 key tuning parameters we're not going to get into, but basically they dictate how aggressively you will respond to errors. And the reason that we have these tuning parameters is because we want to have controllers that are both robust and high performance. And so what robust refers to when you're designing a controller is its ability to maintain a set point and be stable. So even if you give it large perturbations, so even if, let's say cold water got completely shut off in the neighborhood or whatever, like a really robust controller would be able to handle that situation and not go into these unsteady situations where you can get just wild fluctuations in temperatures. So robustness is that. Performance has to do with how quickly a controller is able to respond to a deviation in the set point. So when error happens, the performance is how aggressively, basically you can think of it as that controller will get rid of that error. And so a high performance controller will be able to very quickly get rid of that error and get you back to that desired set point, which in our case would be 100 degrees Fahrenheit. But there's a huge trade-off, and this is the balance and the nuance of process control, which is, when you're building these controllers, you need to optimize between performance and robustness, and you can't have the two. Like you need to decide what you want, and you do the best you can with what you have, and that's what engineering is all about. So basically, if you had a controller that is very robust, it's going to be very low performance, and vice versa. If you had a controller that was really fantastic at keeping you super close to that set point value, it's all going to be very quickly it can go into these unsteady extremities, and so it's not robust. And so those are types of things you'll deal with. Another thing that's very interesting to think about just in this little story is feed forward control. And so like as you're taking the shower, let's say you heard the your brother flushed the toilet, and you know what that means, like what's going to happen. And so in that case, you're making use of an additional input that you've heard to try to compensate for that, to make sure that you're not going to allow that set point or the actual output to deviate too much between when that impact happens. And so that's feed forward control, is before it even affects the output, you are responding to that. You're trying to account for the dead time. So if you are fairly confident that it's going to take about 5 or 10 seconds before the drop in cold water pressure up on the second level of this home, for instance, is going to impact the water temperature on this first floor, then you can build this into your PID controllers using these generally they're denoted with theta, but these are the types of things that you'll be doing in a process control class that make it pretty interesting. And for me, I personally really need to be able to relate these things back to stories, like actual living real life stories, because otherwise I think you'll find, at least for me, like it can get very kind of dense mathematically and hard to follow. So as long as you remember these things, like set point is what I want. Like I want the water to be at this value. Air is what happens when the water's not at this value, and there's consequences of that. So, in your case, you get burned. If we were running a chemical process, for instance, we would have a lower yield in our process because the chemical engineers have told us that, we need to have the inlet feed be this temperature and this pressure. So if it isn't, we're not going to be getting optimum yield. We're not going to be getting as much ROI as we can for our investors, and it causes lots of problems. So process control is an incredibly important topic to understand for engineers in general across disciplines. And so I'm going to be wrapping things up with that, but I hope this is interesting. And if you guys have any questions, let me know. But thank you all for watching. I hope everyone out there is doing well, and I will talk to you guys next time.